Morning, everyone. So we're going to continue our overview summary. Today we're going to take a look at our chapter on organic. Now I know this is the last chapter that we've been working on, so it should be still very fresh in your head, but let's just go over some of the main highlights. Remember, organic chemistry is focusing on the chemistry of carbon. We started off saying what makes carbon so special is carbon starting off with 4 unpaired electrons. Usually it's the unpaired electrons that end up doing the bonding, so right away carbon can actually make 4 attachments. Carbon also has a special property called catenation, where carbon can actually bond to itself many times. So let's just tack on a few other carbons here. We can form a long carbon backbone. We can start forming rings. We can start doing double, triple bonds. We get a lot of variety in organic chemistry. But no matter how things are bonded, we should always be able to spot where carbon's 4 unpaired electrons ended up. So for example, these middle carbons here, it's using 2 electrons to hold the neighbors. That implies that I should have 2 extra arms here. Unless otherwise specified, you imagine that the rest of the bonds here are attached to hydrogens. Other elements that came along later on, we saw functional groups that ended up having oxygens. We saw like double bonded oxygens for aldehydes and ketones. We saw nitrogen with amine. It's possible to have other elements, but primarily we're based off of a carbon backbone. We start off here looking at different families, trying to learn a little bit of the naming of it here. Our first family, we had called them were alkanes. The ending here was A-N-E, where everything here is just all single bonded. We even looked at a subset of these alkanes, only focusing on the hydrocarbon kinds, where hydrocarbons are a family of organic molecules that only contain 2 elements, hydro for hydrogen and carbon for the carbon part. We say alkanes are saturated. That word saturated means we have the maximum number of attachments. Because things are single bonded, at a maximum, this is however many hydrogens I can end up holding. We have what's called the general formula to make a quick prediction. How many hydrogens should there be in this saturated molecule? Remember the general formula here for an alkane, it doubles the number of carbons, and then it adds 2. That just assumes that most of the carbons here should have 2 H's along the side. The 2 that are exceptions here are going to be the terminal carbons, the ones on the ends. Because they're only holding the chain on the one side, I can actually hold 2 extra side hydrogens, so that gives me the extra plus 2 there. So we started from long chain molecules, we started looking at different prefaces as the parent name. We count up the longest strand of carbons that we can connect together. Remember, organic, for the parents at least, for 1, 2, 3, and 4, they changed it up a little bit. Where we would normally expect the mono, di, tri-tetra, they prefer methyl, ethyl, propo, butyl as the endings. We utilize those for the alkyl groups as well, but meth, eth, prop, but for 1, 2, 3, 4. We saw later on the mono, di, tri, tetra come back in another place. In terms of these substitutions here in general, you can call them alkyl groups. Now, if I just called them alkyl, you can imagine that they are carbon branches along a trunk that is your parent, this really long strand molecule. We can actually branch off carbon groups. Maybe 1 carbon groups, maybe 2 carbon groups. For all single bonds, they allow for free rotation. So this molecule here can be twisting and flopping around. Fortunately, the way of naming that we talked about, always finding the longest chain, always keeping the numbers tiny, we should always end up with the same name, no matter which side we're actually looking at this from. So, in terms of how many carbons are on the branches, we utilize those same prefaces. Because alkyl ends with the suffix here YL, we're going to end off methyl, ethyl, propyl, that same YL as the ending. We could also use alkyl groups here as alkyl halides. Halides utilize our halogens, our group 17 nonmetals there. We're going to use the ending here O instead, fluorochlorobromoiodo. If I happen to have a molecule that happens to have many different branches, remember I end up alphabetizing them, and then we'll just need to tack on a number just to specify which branch occurred where. Okay. So again, as I alluded to, the naming scheme was devised by this group here, IUPAC. IUPAC stands for the International Union of Pure and Applied Chemists. The only reason I bring that up here is sometimes you say, write the IUPAC name for this molecule. It's the naming rules that we know. We find the longest carbon backbone, don't double back on yourself. We number our parent to identify all the different branches, and if we can, we choose to keep numbers as tiny as we can get them, right? So let's just try a molecule over here. Let's just string together a bunch of carbons. It's not always necessarily going to be the one that's left to right, but you can just sort of tack on however many of these attachments you want here. Let's say we have that. I'll even sub on maybe a, I don't know, fluorine group. Okay. Right. So this molecule happened to sort of twist itself into this weird sort of configuration. First thing you want to do is you want to find the longest carbon chain. So you can go from any side to any side. I can start from here. I can go 1, 2, 3, 4. Well, shouldn't. It has to be something longer than that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. I probably actually want to start from this far side here. Maybe 1, 2, 3, 4, 5, 6, 7, 8. So good. 8 is the longest chain here. I usually like circling the parent so I know what's covered by my 8 already. Okay, so we have that 8 there. That longest carbon chain, I look up the prefix. So 1 to 4 was a little bit weird, but 8 is still octa. This is going to be the very last word in the name. It's going to be octane. I am an 8-carbon alkane, where everything is single bonded. That covers everything in the green circle there. And we have a couple different substitutions, a couple different branches that sort of go off to the side of the molecule here. These are 1-carbon branches. So we're going to call each of these branches here methyl groups. This one here by itself is a 2-carbon branch, so we'll call that an ethyl group. This F here is a halide, so that is actually a functional group here, but it's a halogen. So we have that halide there. And then we just need to number our parent, so if we can, keep the numbers tiny. If I number it from top to bottom, my branches are at 2, 3, 4, and 8. If I number it from bottom up, I already have a branch at 1, so probably I want to number it in this fashion here. Okay. We'll notice as a branch here, because fluorine here doesn't have a carbon associated with it, so it's not holding other hydrogens secretly like this one is. Okay, so those one you might see CH3s and whatnot to imply the condensed formula for all the hydrogens that they're hiding away. The halogen here does have extra lone pairs, but it is just a plain old F atom. The F atom here can be added to the end of the chain because it doesn't extend the chain. So that's going to be position 1. Seeing as I have these different groups here, I'm going to alphabetize them. So we have F for the fluoro, E for ethyl, so ethyl is going to come first. That's going to be at position 4. So let's go 4-ethyl. If I have numbers and letters, they're always separated by hyphens. Then comes my fluoro. So my fluoro is at position 1. It's okay that these numbers in the word name here, they look out of order because more importantly here, I'm focusing on the alphabetizing. I have 2 methyl groups here. I could totally have said 6-methyl and also 7-methyl. Seeing as I have 2 identical groupings here, I'm actually going to condense that into a dimethyl, but I'm going to still show the numbers here. Numbers and numbers are separated by commas, so 6, 7. I'm going to use that dimethyl to tell me there are 2 methyls somewhere in the picture. One of the methyls on 6, one of the methyl on 7. And when we alphabetize here, although sometimes we throw in di, tri, depending on how many that we have, we still alphabetize it based on the branch name, in this case here, methyl. So there's that full name there. For the very last parent, you can even either hyphenate it or just ram it into the parent name, but we're just sort of substituting this octane here. We've given all the information to draw that molecule there. Okay. So see a couple other highlights here. We've talked about the notion of being saturated or unsaturated here. Saturated meaning you have the maximum number of attachments. Alkanes are saturated. Alkanes having single bonds, they twist freely. So this alkane doesn't always need to twist in this fashion. It can sort of unwind and whatnot. Things start to become unsaturated when we start losing hydrogens. There's 2 main ways we can get degrees of unsaturation. Imagine taking, let's take butane as an example. Imagine taking butane, which started off saturated, which started off with all of its attachments. For us to start losing hydrogens, what you could do is you can actually ditch the 2 hydrogens on the end, and you can use those 2 unpaired electron, and you can actually end up forming a ring. That's referred to as a cyclic compound. We're actually going to use the prefix cyclo before the parent. When I end up forming that 4-carbon ring, as my example here, this is going to be called cyclobutane. This one here is 2 hydrogens less than my actual butane. So we are in structural isomers, but we have formed a ring compound. For our simplicity, our molecules will only have 1 ring, and the ring is always going to be the parent. Even if I later on have carbon chains that are extended to it here, those would be treated as branches off of my parent ring. So just remember to add the cyclo as a prefix. I could also introduce a degree of unsaturation here by making multiple bonds. If I took any of these single bonds and started making a double bond or started making a triple bond, every time I go from single to double, I lose 2 hydrogens. Going from double to triple, I lose 2 hydrogens. I could have a large molecule that actually has many different double bonds, many different triple bonds. Every time I form that double bond, I lose hydrogens. Okay. So moving on from there here, we started surveying over a couple other families here. We started looking from alkanes over to alkenes. So the ending here is ene. Most people remember alkene means double bond, but specifically that double bond here has to be between 2 carbon centers. So we have unsaturation here, our general formula, which used to be 2n plus 2. If we assume our alkene only has 1 double bond, I've lost those 2 extra ones. Now my general formula has reverted down to H2n. If you go even farther then, an alkyne with a YNE ending, this one will have a triple bond. Again, that triple bond specifically has to be between the 2 carbon centers here. I lost yet another 2 hydrogens. In doing that here, you'll notice my general formula has changed. Those ones there, as general formulas, assume you only have one of the double bond or one of the triple bond, which we'll do for our course. Okay. Both double bonds and triple bonds here, we say that they are rigid. We say that they don't twist very easily. So it gives rise to a very special type of isomer for alkenes. Because the carbons involved in the double bond, because this double bond here doesn't twist, I'm going to actually be concerned with which side in this molecule here, I'm holding a methyl and a hydrogen group, which side are the methyls and the hydrogens pointing relative to the other side. If I happen to have the hydrogens pointing the same side, we're going to call this the cis isomer. Cis means same side, okay? We're going to add that as a prefix that comes at the really beginning of the name. If the hydrogens are sort of across from each other here in math class, that would be our transverse, that would be our diagonal. This is suddenly going to be our trans isomer. Okay? So while naming wise, we might still need to do, well, let's find the longest chain. Remember for an alkene, we want to make sure the longest chain cuts through the double bond or the triple bond. The double bond or triple bond takes priority, so it takes the smallest number if possible. And then just to identify cis or trans, just focus on alkenes, zoom in on what the carbons are holding. If they are holding 2 similar groupings, like in this case here, they're both holding hydrogens, let's just point out whether they're on the same side, both point in the same direction, or pointed opposite to each other. Now, it's not going to take much for us to lose cis-trans isomerism. For example, let me draw a molecule over here. Let's say C double bond C. Okay. What if I have hydrogens on both of this carbon, and then very similar to my other molecule here, CH3. Okay. No doubt this double bond here is rigid. That part there doesn't twist unless you chemically break that bond. But this time, because I can't tell the difference between this H or this H, I wouldn't be able to tell you whether the H's are on the same side or whether the H's are opposite. If you really wanted, let's say, this methyl extension here to be on top, I would just flip this molecule just upside down, and suddenly the molecule would have the CH3 above. I would have no cis or trans. Another reason why I might not have cis or trans, we're relying on the fact that we have both carbons holding the identical group. What if both carbons don't hold identical groups? What if instead of these being similar here, what if I swapped on, let's say, a fluorine, I swapped on a chlorine here. Now all the groups are different. Again, in this case here, well, you can't point. Are the similar groups same side, both opposite side? Well, they aren't similar groups at all. Okay, so definitely no cis or trans. Chemists have sort of investigated this issue here. What they've started doing later on is they started, yeah, I know that these groups here are different. They started introducing a priority order. They started ranking these branches here, which one is more important. So what we're going to do here is we're going to actually say, just based on atomic number, fluorine is atomic number 9. This is only 1. This is the high priority group. Between chlorine and carbon, chlorine is the high priority group. I know fluorine is not chlorine, but seeing as both high priority groups are pointing in the same direction, this is more like the cis isomer than the trans isomer. We're actually going to use E and Z. Z actually means the same side, so this would actually be perhaps the Z isomer, sort of like the cis isomer that we've seen before. Okay. We only have cis and trans for alkenes because both of the carbons potentially hold 2 neighbors. By the time I get a triple bond here, seeing as I'm using all 3 of my unpaired electrons to hold each other, that only leaves me 1 extra arm to hold the neighbor. These neighbors here, if you look at the geometry, they have to be straight across, they have to be linear anyways, so I'm not going to have, oh, they're both on the top or both on the bottom of the double bond. I'm always holding things that are just straight across that way. So only sister trans, we call them geometric isomers only for an alkene. Okay. As we finish up this chapter here, we looked at a few other functionalities. Functional groups here are special groupings, special molecules that groupings that this molecule might have. It gives a molecule very particular behavior. Some of these molecules here you need to know the full names of. So for example, aromatic compounds are based off benzene. Benzene here was a 6-carbon ring. Remember, we're not benzene until we have what's equivalent to double bond, single bond, double bond. That's sort of alternating for us there. This molecule here is actually in resonance, okay? Benzene, we already know is a cyclical molecule. It already is a ring. So you'll notice the ending here doesn't say cyclobenzene. If I start substituting, if I start subbing on, let's say a methyl group, let's say a chlorine group, things like that, I would just put methyl and then chloro off of benzene as the parent name. Okay? For alcohols, they all have the special grouping here, an OH grouping. And OH, in the word name, they'd end up with OL, so methanol, ethanol, things like that. Just like we would have to number where the double bond or triple bond comes in, we want to number where that OH group here comes in. Esters were the other grouping here that we also named in detail. Esters have this C, double bond O, single bond O functionality. This is one of the functional groups that sort of comes in between a chain. Although I could worry about long chain, short chain here, because this always comes in between 2 chains, IUPAC has basically come along and said the carbon side of the molecule, including the carbon in the middle here, the carbon side is going to be considered the parent. The oxygen side is going to always be considered the branch. As a branch, it's going to have an ending YL, right, like methyl, ethyl, like that. As the ending for the parent, we're actually going to change it to O8. So we could have like methyl ethanoate or propylbutanoate. Okay. Be careful, this molecule here might be twisted in such a way that maybe if they draw a skeletal structure here, they might draw it double bond to O, and then single bond to O, and then we have a chain that's sort of branched off there. We could still name this here, the COO functionality is right here, and we can still say, well, the carbon side of it is still going to be the parent. Our parent here happens to have 3. The oxygen side of it is the branch. This one here only has 2. So this one here, I would have called it ethyl. And I'm going to use propanoate for the carbon side. Okay. The very last functional groups here, we have aldehyde all the way down to carboxylic acid here. These ones here, if I'm drawn a structural diagram here, I just need to label them. I just need to circle them. I've sketched them, what some of these look like for you there. You need to memorize the family name as well as the functional group associated with it. Okay, so hopefully that helps you with your review. Just let me know if you have any questions.